Good afternoon, everyone. We are Group 17, and today we'll present our project on predicting 30-day hospital readmission. Our presentation is structured into 5 main parts. I'll walk you through the first 2 sections, and my teammates will cover the following sections. Let's begin with part 1, the introduction. The data sources include tabular EHR, which is electronic health records, imaging features, and clinical notes. Due to the limitation of our computational capability, we chose to dismiss the imaging feature part in our project. We wanted to validate the feasibility of this task. Here, we plotted the readmission rate against the patient age, which is one specific feature in the EHR dataset. The red line clearly shows a positive correlation between them. This confirms that our clinical features are indeed predictive of the outcome, which lays a solid foundation for our project. The dataset is split into training, validation, and test sets to ensure robust evaluation, and our primary evaluation metric for the study is AUROC. Moving on to part 2, data processing. Before we delve into addressing raw data, let's first investigate the characteristics of the dataset. It's worth noting that the readmission rate is about 23%, which is a class imbalance we needed to address afterwards. The table from below is an example of the EHR data from one patient, where one row represents 1 day and columns show various indicators. There are 4 distinct categories among the 171 raw features: demographics, laboratory tests, medications, and diagnosis, or ICD codes. Moreover, we found a clear distinction. Demographics, ICD codes, and medications are almost entirely static, which means the data rarely change during one stay of a patient. In contrast, lab tests are mostly dynamic, fluctuating daily, which reflects the patient's real-time physiological state. On the right, we see that there are many binary features, although treatments are mostly non-binary since it records the actual dosage. Driven by that analysis, we adopted the following strategy. For static data, we extracted the last value, as averages would be meaningless for stable features. For dynamic data, specifically lab tests, we calculated standard stats like mean and standard deviation. However, we introduced a specialized interaction term, slope times days. Since the slope represents the speed of change and days represents the duration, multiplying them reveals the total magnitude of health change during the stay. This makes the feature much more interpretable and robust against different length of stay. Finally, for clinical notes, we applied TF-ITF vectorization to convert text into numerical features. Overall, our feature dimension is 972.
Given the features as our input, here's the model we chosen to do the experiment. We have 4 approaches: XGBoost, CatBoost, Light GBM, and Model Fusion, which is a combination of the 3 model. Since our dataset is not very big, so we did not choose those complex neural network model. We only use traditional machine learning models. And the first model is XGBoost. For the training method, we utilize 5-fold stratified cross-validation and negative-positive ratio to overcome the issue of imbalanced data. We use the training set to find the best hyperparameters, and we will combine the training and validation set to train the model. Lastly, we will use the model to predict the testing set. We use a function called trial_suggest_float in library Optuna to find the best hyperparameter combination wisely for us. Here are the best hyperparameters. After the training, we can see that the following results. The AUC of validation set is 0.789, testing score in Kaggle is 0.82. And actually, we have tested that combining training and testing set for 5-fold stratified validation does not help a lot. And the next model is Light GBM. We did a same experiment. We have different hyperparameters. We can see that the validation AUC is slightly lower, 0.7814. Similar to CatBoost, we have slightly lower validation AUC, 0.787, so as testing score in Kaggle. Lastly, we try to utilize the difference among these 3 models to enhance the stability of the final prediction. We use rank averaging to combine the result of the model because models have large output values or variance will dominate the result. So we ignore the specific probability values predicted by the model and only focus on the relative ranking of the samples in the prediction result. And we can see that the results have only little improvement. The potential reason is that they are all gradient boosting decision tree architecture. They tend to share similar decision boundaries and error patterns. And also, only the lab features in our dataset are changing throughout the period. The other three type of features, like demographics, ICD, and medications, are constant, so we cannot do so much feature expansion. Therefore, our future model has been chosen as the final model.
Moving to part 4, model interpretation. We know that the model works. This section will explain why. First, let's look at the decision logic using the simplified surrogate tree. We build this tree to approximate how our complex model thinks. You can see the various splits at the top is based on both PO2 and lactate. This tells us immediately that the model isn't just looking at random data. It is prioritizing respiratory status and metabolic stress right out to the gate to distinguish between safe and at-risk patients. We confirmed this logic with our global feature importance analysis. In this chart, the red box highlights dynamic features, those that track changes over time. The single most important feature in our model is pH bud slope date. This is a crucial finding. It proves that the trends of a patient's health is far more predictive than their status at a single moment in time. Now, this brings us to our core insight, normal trend. A patient might look stable on paper, but if their trend line is crashing, the model knows they are in danger. We group these risks into 4 categories. First, physiological stability. The model sees that a normal pH at the discharge is unsafe if the patient has been trending rapidly towards acidosis. Similarly, high variability in PCO2 indicates the patient is struggling to maintain respiratory stability. Second is metabolic stress, driven by lactate. Lactate is a marker for sepsis. The model found that if lactate isn't clearly declining or if it's fluctuating, the underlying infection or shock hasn't resolved. The patient is living with heightened stress. Third, variety. The model flagged specific medications. Antibiotics at discharges suggest a severe, partially treated infection. Vitamins were a strong predictor for malnutrition and general variety. Finally, oxygen capacity. A downward trend in hemoglobin, even if the level aren't critical yet, suggests a occult bleeding or marrow failure. To conclude, our model succeeds because it acts like a clinician. It understands that direction matters more than the position. It doesn't just ask if the patient is okay now, it asks if they are staying okay.
In this part, we'd like to have a future discussion about potential good features in real situations. From our dataset, we can see some limitations compared with real-world data. Especially, our dataset does not include any information about the hospitalization time. However, based on the subject ID of each patient, we can actually see some patients have multiple hospitalization records. This actually inspires us to ask, can we use a patient's historical hospitalization records as a new feature to improve our prediction accuracy? And to explore this idea, we made some informal experiments. Based on our previous feature engineering, we added only one new feature, patient visit count, which can simply count how many times a patient gets into the hospital, and then we treat the same model again. Surprisingly, the AUC score improved greatly, from 0.82 to 0.89. Well, however, since our dataset does not have any time information, this feature is actually illegal. It causes data leakage because it uses information that includes both the future and past visits of the patients in the test set. Well, still, this result strongly suggests that a patient's historical hospitalization record would be a very important feature in real scenarios. And also intuitively, such data reflects the patient's previous physical condition, which can be a key indicator for the prediction. Therefore, in real-world scenarios, if we have access to patients' historical hospitalization records, there will be an excellent source of predictive features. So that's all for our presentation. Thank you for listening.